Okay, let's take a look at the series n divided by the root of n cubed plus 1. We're going to take the summation of this from 1 to infinity. And we're going to try for the direct comparison test. So the plus 1 doesn't matter as n gets big, so we can drop that. Our job is to go out and get another series, b sub n, that will mimic the behavior of our series, essentially. So the numerator has only the one term. We can't drop anything there. The denominator has the plus 1. So we go to drop that. If we drop that, we have the square root of n cubed in the denominator. That's not the 1/3 root. That's not n to the 1/3. What that is n cubed to the 1/2. It's n to the 3/2. So we have n to the first power divided by n to the 3/2, and that will reduce to be 1 over root n. Okay. Make sure that as soon as you go get your series, you know what, as soon as you go get your b sub n, you know what the series on it does. This is a p series. This is 1 over n to the 1/2 power. P is equal to 1/2. It diverges. Now, when you go out and get a series that's divergent, the inequality should go the following way. Yours should be less than the given. But this doesn't work out. Okay. You could either do it by cross multiplying. Be careful when you cross multiply over an inequality. The placement of the terms matter. Or you can just sort of reason it out. How this guy here basically has a bigger denominator, so it's smaller. We're trying to compare basically n cubed plus 1 to, if we go to unsimplified version of it, the only difference is the plus 1. And that plus 1 makes this guy have a larger, slightly larger denominator, which in turn makes the whole thing smaller. So it's going the wrong way. If you were to do cross multiplying, it works. What you have to do is keep, when you cross multiply, whichever side the numerator is on that you're multiplying by, you have to stay on that side. So that's how we end up with the root n cubed plus 1 being on the left and the root n to the 3/2 being on the right. That n to the 3/2 came from multiplying n by root n. Either way it goes, the inequality is going the wrong way. What do we do when the inequality is going the wrong way? Basically, the direct comparison test doesn't work. We need another test. Similar to what we did for improper integrals, along comes the limit comparison test. It's not concerned about inequalities going a certain direction. You'll be given a series called summation on a sub n, and you'll go out and get your b sub n the same kind of way, and make sure you know what it does. Now here's how the test works. When you go to divide the terms of the given series by yours or vice versa, if you end up with a constant finite positive number, then you can conclude simply that the two series will behave alike. So if yours converges, then the given one converges. If yours diverges, then the given one diverges. But what's nice about the limit comparison test is that it says even more. It says that when the limit of the an over bn is 0, and at the same time your series converges, then you conclude that the given series will also converge. Okay, so it allows for the limit to be equal to 0 if you pair that up with the fact that the summation of the series that you went out and got, the summation of b sub n also converges. But it even says more. It even allows for the limit to be equal to infinity. If you pair the fact that the limit of an over bn equals infinity with the fact that your series diverges, the one that you went out and got, then you can conclude that the given series a sub n also diverges. And so this is the limit comparison test. It has no worry about an inequality going one way or the other. Let's take a look at the series that gave us trouble before. We go out and get the same b sub n. We use 1 over root n. And now we consider the limit. So we take the given n over root n cubed plus 1 and divide by 1 over root n. Alright, so the algebra is going to get a bit messy here, but we can do it. Just be careful. So when you go to multiply by the reciprocal, what that essentially does is that will make the power on n in the numerator be n to the 3/2. You're multiplying by the reciprocal. So you're taking n over root n cubed plus 1 and multiplying it by root n. These guys combine to give you n to the 3/2. Okay, great. Now we need to see what this limit does. Algebraically, we're going to attack this by focusing our attention on the highest power on n in the denominator. It might look like n cubed, but it's not. It's actually n to the 3/2 power. And so we multiply both top and bottom by that reciprocal, 1 over n to the 3/2 power. And what we end up getting is it's better to represent this guy in the denominator. Well, of course, in the numerator we get a 1. These guys multiply to give you 1. In the denominator, if you represent this guy as the square root of n cubed, then we can combine these together. We'll have root of n cubed plus 1 divided by root of n cubed. Make that into 1 root and then break it apart. So make that into 1 root and then break it apart. And you end up with exactly 1, because the 1 over n cubed that was part of the denominator there, it goes to 0. As n gets large. Alright, so what's the result? Well, we did the limit and it equals 1. That's a constant. A finite constant. And so, according to the limit comparison test, it says that the two series will behave alike. Your series diverges. It's a p series, we saw before. So, the given series also diverges. Okay. We'll have another video that has 2 more examples of the limit comparison test.